Okay, AP Physics 1 students, this is the start of our second unit. Once again on kinematics, or the mathematical or scientific description of how objects move. Now remember, we're not focused on why objects are moving, we're just trying to describe how they move. Now previously, we were focusing entirely on graphing, but now this next unit is going to be focused on the kinematic equations, and specifically projectile motion, which will be getting into two-dimensional kinematics. Today's lesson, though, is going to be focused specifically on the kinematic equations. Now, previously, when we've been working with motion graphs, we've tried to solve for a bunch of different things. How far has an object moved? How fast has it moved? How much is it accelerating? And we've done that exclusively using graphs. But now we're going to find a more efficient way, and oftentimes a more practical way, to solve those same problems without having to go all the way down the rabbit hole of creating graphs to do so. So let's start with a problem. Let's say we have a Formula 1 racing car that's accelerating from rest to 83 meters per second, and to put that in perspective, that's about 185 miles per hour over 345 meters of a straight track, so no turns. We want to know what is the acceleration of the car. Now, last unit, whenever we would look at something like this, we probably would have started off by building a couple of graphs, a position versus time graph and a velocity versus time graph. Now, if I look at the position versus time graph, we know that since it's speeding up, it's probably going to have a shape that looks something like this. But you'll notice that we kind of have an issue here. We know it goes from 0 to some distance, but we don't know what time this occurs at. And similarly, we could build a v versus t graph, and once again, we know it goes from 0 to some speed, but we also don't know what time that occurs at either. Now, I want to be clear, we could solve this problem using these graphs, but it would be a little convoluted. There'd be a lot of extra steps, and it could take us quite a while, and it would really have to make sure we were graphing things really precisely. So let's look at a different way that we can try and do this, which is through the use of 4 specific kinematic equations. Now, before we start discussing what these 4 equations actually are and how to use them properly, there's something I want to talk about for a second, because these are really the first somewhat complicated equations that we've learned in AP Physics 1. Now, a big reason why I want to talk about this is I want to really emphasize that all equations in physics come from somewhere. And that probably sounds a little ridiculous. You're like, well, of course it comes from somewhere. It doesn't just pop into existence. But that's often how equations are presented. They're often presented in such a way as being fully formed. You have no idea where they come from. And they're kind of just like little magic tricks that we put numbers in and we get numbers out. But that's not really a useful way to think about them. So always in this class, we're going to talk about, well, what are the basis for these equations? And it can be many different things. It can be physical laws that we're going to discuss. It can be experimental evidence, symmetry, which may sound a little strange, but symmetry guides us a lot in physics. Theoretical models that we've been exploring, maybe even a thought experiment. That's a little bit more of what we're going to be doing today. And sometimes even other equations that we can put together and get new equations. And sometimes, you'll be able to formulate these equations, and they're only going to be good for certain instances, but sometimes we can get much more broadly applicable ones. And to create these, we combine all of these pieces of information into something called a derivation. And that derivation shows us where the equation comes from. So what we're going to do before we actually learn the 4 kinematic equations is we're going to derive where exactly they come from. So let's start off by deriving equation number 1. I want to be clear, these 4 equations, they don't go in a particular order. I'm going to call them 1, 2, 3, 4 in this video, but they don't really have specific names. They're just the 4 kinematic equations. So we're going to start with a v versus t graph, and we're just going to have a nice straight line on here. And let's remember some things we've learned about these graphs from the previous units. Well, we know for a fact that this y-intercept is going to be the initial velocity, v naught. We know that it's going up to some point here, t comma v, so that is our final velocity at some time t. And additionally, we know that the slope of a v versus t graph gives the acceleration, which we typically abbreviate with an a. So let's just write out the equation for this line, y equals mx plus b, with the appropriate variables. Instead of y, I'm going to have v for velocity. Instead of m, I'm going to have a for acceleration for the slope. Instead of x, I will have the variable t, and instead of y-intercept b, we're going to have v naught. And now I'm literally just going to rearrange this a little bit and write it into a form that is a little more common, which is v is equal to, I'm just going to flip these two, v naught plus at. And congratulations, that's literally the first kinematic equation. So let's move on to the second one. Now, once again, we're going to look at the same v versus t graph. Well, what's another thing we know from this graph? Well, we know that the area underneath it is going to be delta x, the displacement of the object. Now, remember, we don't know the initial or final position, but it tells us the change in position of the object. Well, if I look at this area, it might look a little complicated, but just to simplify things a bit, I'm going to break it down into a rectangle and then a triangle. And we know that the total delta x is going to equal the area of the rectangle plus the area of the triangle. So let's go ahead and add these pieces together. So for the area of the rectangle, we would do base times height. And the base, so if I want to say, actually, let's do base times height. And the area of the triangle is going to be 1/2 base times height. So for the rectangle, the base and height are going to be v naught, this distance here, and t, that distance there. So I'm going to have v naught times t plus 1/2. And if I look at this triangle, I have what? I've got t for the base. And then additionally, I have, well, okay, well, what is the height here? Well, that height is going to be v minus v naught. So this is v minus v naught. So let's stick that in. And you might be thinking, okay, well, that looks a little complicated. That's not really helping too much. But let's actually stick in the equation we just learned, or it's otherwise known as the definition of acceleration. A is equal to v minus v naught over t. So if I have v minus v naught over t, if I just wanted this part here, let's multiply the t across, so I get at equals v minus v naught. And let's stick this into this previous equation. So now I have v naught t plus 1/2 t times at. Now let's simplify it a little bit. Now I'm going to say v naught t plus 1/2 a, and then t times t would be t squared. And this is actually our second kinematic equation. Delta x equals v naught t plus 1/2 at squared. Now moving on to equation 3, we're going to start with the same graph, and we're going to once again look at this v versus t and remind ourselves that the area underneath it is delta x. Now, the previous way we broke down this area was we said it was a rectangle and a triangle, but if we look, this is also the shape of simply a trapezoid. Alright, so now, to make that a little easier to analyze, because usually when we do a trapezoid, we usually have the angled part on the side, I'm going to briefly rearrange it. I'm basically just going to say take this trapezoid and rotate it so that I have, for instance, this side up at the top, this side on the right, etc. So I just rotate it so it'd be a little bit easier to analyze. And I'm going to say delta x is equal to the area of the trapezoid. And if you don't remember the equation for the area of a trapezoid, it is 1/2 base 1 plus base 2 times the height. And let's stick in numbers here. So I have 1/2, and if I look at base 1 and base 2, this would be base 1, this would be base 2, which if I look is v naught and v. So I have v naught plus v, and the height, which would be here, is this distance, t, and voila, we now have the third kinematic equation, v naught plus v. Delta x is equal to 1/2 v naught plus v times t. Now be very, very careful. A common mistake I see is because we're used to doing v minus v naught. Remember that this is a plus sign, so be careful of that. For the final kinematic equation, we're going to go in a slightly different direction. We're not going to start with the graph, but instead we're going to start with two equations we already just derived. number 3, and number 1. So if I look at these, I actually am going to start over with this one for a second, and I'm going to rearrange it in terms of t. So to get t by itself, I'm going to do v minus v naught, move that across, then divide both sides by a. That's going to look a little random, but what I'm going to do with this is I'm going to take this t and now stick it over into this equation. So now I have delta x is equal to 1/2 v naught plus v, and now I'm going to stick in for t v minus v naught over a. Alright, so now what do? Well, I've got this 1/2 and this 1 over a, so I'm going to multiply both of those across. So I'm going to get 2a delta x is equal to v naught plus v, v minus v naught. Which, if you look at this, it should be very, very familiar, because this definitely looks like the type of thing you might be factoring in an algebra class, for instance. So we're going to FOIL this first outside, inside, last. So I'm going to get 2a delta x is, let's see, I've got v squared, I've got plus, what, v naught, minus v naught, and then lastly, minus v naught squared. But if I look, those cancel out. So I'm left with v squared and v naught squared. So I have 2a delta x is v squared minus v naught squared. Now I'm going to move that across. And now I'm just going to rewrite it. I'm going to write this part on the left-hand side. But I have v squared is equal to, I moved that across, v naught squared plus 2a delta x. And congratulations, that is our final kinematic equation. So now we have just derived the 4 kinematic equations. 1, v equals v naught plus at. 2, delta x equals v naught t plus 1/2 at squared. 3, delta x equals 1/2 v plus v naught times t. And 4, v squared equals v naught squared plus 2a delta x. And specifically, if we look at all of these equations, we have these variables here. Time in seconds, v naught is the initial velocity in meters per second. V is the final velocity in meters per second. A is the acceleration in meters per second squared. And delta x is the displacement in meters. But there's one really important qualification here, and that is that these equations only work in situations where the acceleration is constant. Now, luckily for us, that's the only type of situations we're going to be really looking at in AP Physics 1, but there will be some situations we see where this may not necessarily hold up, but for right now in this unit, we should be okay all the time employing these 4 different equations. Well, now that we've derived these equations and we look at this previous problem, the one about the Formula 1 car that I said at the very beginning of the video, your first thought might be, great, I now have these equations, but how do I use them? And how do I know which, there's 4, how do I know which one I should try to use? Because trust me, in most situations there will only be one equation that can really help you out. So now I'm going to introduce a method, a problem-solving strategy that allows us to utilize the kinematic equations effectively. And I want to really add that actually this problem-solving strategy is good for the entire year. Some aspects of it might change slightly, but this is really a very good way to start every math-based physics problem. If you're given some exercise that has math in it, that involves some calculations in an equation, I highly recommend starting with this method, going through the steps, and 99% of the time, you'll be fine. So it is called the guess method. Now, I want to be clear, because I always have someone ask this, this does not mean guessing. It is not guess and check. Does not mean that. Instead, it's a method, guess is really just an acronym to go through a series of steps. So first off, we have G, which stands for givens. So when you read the problem, identify the given variables, the numbers that they give you. And you have to be specific about this is the displacement, this is the acceleration. You have to be able to recognize which is which. Next step is U, the unknowns. recognize the unknown variables. Now, one of those is going to be the variables that you want to find. Occasionally, though, there will also be other variables that you don't know, then it might be good to note those down too. E stands for equation, which is selecting the proper equation. Now, right now, that means selecting the proper of the 4 kinematic equations, but it'll get even more complicated when we learn more equations down the line. The first S stands for solve. Take the equation and algebraically manipulate and solve it for the unknown variable that you want to find. And lastly, the last S is substitute. Take this manipulated equation, put the given variables into it, and then you should just be able to plug those into a calculator, and boom, solve the problem. Now, probably the step that causes most people to pause a little bit is, well, which of the 4 kinematic equations do I use? And what I want you to recognize is that if we look at these 4 equations, all of them are missing one of those variables, either displacement, final velocity, acceleration, or time. All of them contain initial velocity, but those 4 variables, each equation is missing one. And you want to choose the equation that only contains one unknown that is specifically the unknown you want. Okay, now it's going to be a little more clear in a second, but a lot of times when you're looking through these equations, a lot of them will have 2 unknowns for the problem you're solving for. And if they have 2 unknowns, it's not real helpful. You can't algebraically solve that for a specific answer, so we want only one unknown in the equation that we pick, and specifically the one we're solving for. Well, now that we've briefly gone through the guess method, let's give it a shot. Let's say we have this Formula 1 racing car accelerating from rest to 83 meters per second over 345 meters of straight track. What is the acceleration of the car? Alright, so first off, we're going to go with G, givens. Well, your givens, we have 3 here. We have 83 meters per second as the final velocity. Now, you may not have recognized this, but rest means that we had an initial velocity of 0, and our displacement was 345 meters. Now, I am going to briefly note, because this is just good, for these kinematic equation problems, you should pretty much always have 3 givens. If you don't have 3 givens, I would recommend checking the problem again. You probably missed one. The next step is U, identifying our unknowns. Now, we definitely know acceleration is one of them because we want to solve for that. But we also don't know T. Now, of these 2, which do we care about? Acceleration. I don't really care about time here. I don't need to solve for that. So I'm going to not worry about that unknown, but it's sometimes good to recognize the other one as well. Now, here comes the tricky part. We want to choose the equation. This is step E. So if I look here, I want an equation that employs V, V naught, delta X, and A, but does not involve T, because if T is in there, I'm going to have 2 unknowns, and that's not helpful. So if you go back, look in your notes, look through those 4 equations, and you should recognize that the only equation that will work is this one here. V squared equals V naught squared plus 2A delta X. There's no T in there, so this is the right equation. Now I need to solve this equation by algebraically manipulating it. So I start here, V squared equals V naught squared plus 2A delta X. And I specifically want the acceleration. So let's solve for that. So first off, I'm going to move V naught squared across. So I have V squared minus V naught squared equals 2A delta X. And then I need to divide by 2 and delta X. So I'm going to divide both sides by that. And that leaves me with V squared minus V naught squared over 2 delta X equals A. I've now algebraically solved for the variable that I want. Now we substitute in, get the right color here, we substitute in, now that I have this equation, I just flip the sides, and I'm going to substitute in the numbers I know. So, V was 83 meters per second squared, V naught squared was 0 squared over 2 times 345, our delta X. And go ahead and take your calculator out, plug the numbers in, and let's see what you get. Because you got to make sure you can use your calculator properly. And trust me, please use a calculator at this point. And if we do that, we should get a final answer of approximately 9.98 meters per second squared. If I wanted to, I could have even rounded that to 10. That would have been totally acceptable. But that, therefore, is our acceleration. And this was much quicker than having to try to do a bunch of different steps with graphs, and a little more foolproof. If I want to double check, I can even stick this number back into a different kinematic equation and make sure all the numbers come out properly. So what are our main takeaways from this video on the kinematic equations? Well, ultimately, there's one huge takeaway. Can you utilize the guess method, givens, unknowns, equation, solve, substitute, to solve one-dimensional kinematic problems? We're only sticking with 1D now. We're going to get to 2D pretty soon, but we're just focused on 1D at the moment. So specifically, we want to make sure we can identify the given and unknown values when we see one of these problems. Can we select the appropriate kinematic equation, which is something that you've got to make sure you're able to do. And additionally, can we algebraically manipulate the equation and solve it for the variable that we currently care about?